I'm John Swain from FEC Energy. We run the GrowSave program. A little bit more about that in a couple of seconds. Okay, what is GrowSave? I think most of you probably know or have heard about GrowSave, it is an AHDB horticulture funded project, and it's funded by two sectors of AHDB horticulture, the protected ornamentals and the protected edibles. And it's a way, it started off as a way many years ago of trying to get some extra benefit out of the research and development work that we've done in the past, and trying to disseminate that information and make sure that people didn't forget about the stuff that we'd done, and a lot of it is still relevant, a lot of it is still useful information. Primarily around energy, but also about climate control and about CO2. And it's to try and stimulate the uptake of efficient technologies. We're in year 3, coming to the end of year 3 of this current 5-year contract. We'd like it to continue, and I'm sure you would, and your feedback is invaluable to that happening. And if people have any ideas as to what might be a GrowSave topic, what events we might run, what topic areas we might discuss and produce information on, then please do let me know. Speak to Ed or myself at the end, or drop us an email, contact details at the end of every slide. Not every slide, you don't want that, at the end of every session. As you can see, our mantra is your one-stop shop for energy information, or horticultural energy saving. So, yes, we've got a website, doesn't everyone in the world these days, growsave.co.uk, nice and snappy. That's where you can go to find out virtually everything that we do. I think everything, all the publications, all the blog feeds, all the Twitter feeds are all on there. We've got a guy that's just started for us. He started about September, October time last year, came from the aerospace industry. And he was telling me the other day, he said, I thought aerospace had a lot of acronyms. He said, it's nothing compared to energy. There are more acronyms in energy than anything he's ever come across before. So we've tried to simplify that a little bit. So there's a glossary of energy terms on the website. If you're confused about kWh or MWH, which kilowatt hours, megawatt hours, or what's a joule, what's active power, or an air handling unit, an AHU, then yeah, there's a glossary of energy terms there. Yeah, hopefully we'll be able to help you through and give you a bit of information as to what those things mean. If you find anything that's not on there, sorry, you won't find anything that's not on there. If you find something that you're interested in that isn't on there, let us know. Or if you think there's something's wrong, please do let us know as well. Similarly on there, there's benchmarking data. We take temperature information and solar radiation information from a couple of sites around the UK, one north, one south. And turn it into degree days, just to try and give you some idea what this year compares to last year. Average temperature is slightly warmer, radiation about the same this year compared to last year, so that's interesting, isn't it? And they're updated on a weekly basis. At the back on the tables, there's copies of Energy News, which is our 3 times a year flyer that appears in your AHDB Grower magazine. Where we try to keep a topical content. Been quite a lot of renewables focus in that in the last couple of years, as you would expect. But also coming, we've got a regular slot for next generation growing for anyone that's interested in that. We try and keep a regular theme running through that in Energy News. We also produce technical updates. We've got technical updates that cover pretty much everything we're going to talk about today. Heat pumps and combined heat and power and biomass boilers, and also CO2 and lighting, next generation growing, use of screens, use of fans. Quite a wealth of information there. We produce 4 of those a year, so there's a good 20 or 30 technical updates there. They tend to be 3 or 4 pages long and take a topic and look at it in slightly more depth and detail than we can do in Energy News. And if you've got any questions about today or about anything else, then all course materials from events are uploaded to the website, and tomorrow we'll post some links. These sessions are being recorded and will be streamed in their entirety via YouTube, but linked from our website tomorrow. And the course materials, the presentation slides, and any other information that's pertinent, we will put up there in time within the next week or so. As I say, we've got another 2 years of this contract left to run for GrowSave. What's coming up? Well, next generation growing is a theme that we're very interested in, or a lot of growers are very interested in, quite topical. Managing biomass boilers, that's a topic area that some people are thinking about, and maybe we're not getting the best out of our existing boiler plant, and is there a way that we can improve the systems, improve the technology and make them more efficient and use less fuel and that sort of thing. Humidity control is a topic that keeps coming back and being requested and talked about, so we'll probably run another basic of humidity control session in the next year or so. Air movement, again, another very topical subject, as is use of screens. The last two feed back into next generation growing, into some techniques there. So that's what we're looking at probably for the next 12 months. Our contract year ends in August, so ends in July, so from August onwards we'll have a new programme of sessions. If there's any topics in there that you think are missing, then please come and talk to myself or Ed, and we'll see what we can do and get them in the programme. So we've had, as I say, we've had renewable heat incentive since 2011. It's been there, it's been exciting. Exciting for some of us. It's not been an easy ride in terms of trying to work out what's available, what's allowable, what's going to happen in the next quarter. Is we're going to have an impact of a digression, and it's not been like watching paint dry. Because you just never know what's around the corner. You never know what the government are thinking and what they're going to change as the popularity of the scheme takes off. What I'm really hoping is that the latest set of regulations, so they've decided to go through a reform. We had a consultation back a year or so ago, and in March this year they laid some draft regulations before Parliament. And I'm hoping that these regulations are going to give some stability towards the end of the renewable heat incentive scheme, which goes on for another 3 years to 2020. Because we can't carry on as we have been doing, going from digression period, one quarter to the next quarter, and having these big rushes, because we just end up with projects that aren't quite considered enough. And the tariff structure has meant that we do things that maybe we wouldn't normally do. And hopefully the way that they've reformed some of these, the biomass boiler sector has been the greatest beneficiary of the renewable heat incentive so far. And I'm hoping these reforms will continue to promote biomass boilers, because I think there's a great deal of potential still left in them, but also try and bring some of these other technologies to the fore, where maybe actually people don't want big lorry movements of fuel in and out of their site, or they have a great import connection, or they have combined heat and power already that they can tie onto a heat pump. And so these regulations laid before Parliament in March. As I say, things are never easy in the life of renewable heat incentive. They got pulled in at the end of March, pulled out of Parliament because there were some issues with the words in them in one area. And of course then we decided to have a general election, didn't we? So they haven't gone back into Parliament yet. They were meant to have been up and running and signed off by now, and they're not. And I'm hoping by the end of the year we will actually see some movement in that, and we'll have some stability again in the renewable heat incentive. Meanwhile, the current scheme continues as it is. So we've still got the medium biomass rates as they are at 5p and 2p, which is the sector where most people are interested in at the moment, and all the other technologies and all the digression caps, the digression methodology and the budget caps, they all continue exactly as if nothing had happened. And so for some there might be a last chance to get a project in under those rules, but for most maybe they'd be better off considering their project in the light of the regulations that we've got here and making sure they're ready to go when the new regulations come through. These regulations aren't laid before Parliament and automatically get accepted. They have to go through a committee, 16 MPs, majority verdict, majority vote to get approved. So at least 8 MPs have got to say that this is okay for it to go through. The key changes that we'll see in the regulations, we've got quite a lot of detail about what's going on. Quite a big one is the merging of biomass boiler tariffs. So we have had the 0 to 200 kilowatt band, we've had the 200 to 1 megawatt band, and the 1 megawatt and above band in terms of the amount of incentive they receive. They're all coming together under one rule, and actually that provides some opportunity, which I'll talk about in the biomass boiler session later on for expansion of projects or bigger projects. An increase in Tier 1 capacity. So for those of you who are familiar with the terminology, you'll know what Tier 1 is, but Tier 1 basically says we'll give you a higher rate of incentive for a small amount of the energy that you produce, and then we'll drop it to a lower rate of incentive to make sure that we're not over-incentivizing any particular technology or giving you more money than actually the project needs to pay its way. There is a section called tariff guarantees. It's something that's happened in the feed-in tariff in the past, where you apply to the scheme before you've committed your project or before you've actually built your project, and you say, right, this is the tariff I'll get once it's built. It's not been available in the renewable heat incentive up till now, but it is something that's coming in. And I'll talk about that in a couple of seconds. Planning permission, that's an interesting slant on the regulations. Again, not something that's been required in the past, but is required now. Changes around combined heat and power efficiency. We believe that's the reasons that the regulations were pulled out of Parliament at the end of March, because there were some upset and some changes that needed to be made around them, and around the digression rules. So digression, I don't think digression is actually a word. If you put digression into a Word document, into an email, all your spell checkers say, do you mean regression or digression? It's a word that often are made up, or maybe it's Department for Business, I don't care who made it up, but digression basically means the rates will come down if the scheme is popular. And if we're too popular, we've got a cap. And we've had a cap for a while, actually. The cap came in under some sort of emergency rules back a year or so ago, but it was one of the key facets of the reform was to make sure that the scheme had enough money left in it to continue to 2020. And some changes around heat pump eligibility and preliminary accreditation for heat pumps, which I'm sure Ollie is going to cover in his session. So merging a biomass boiler tariff, I'm not going to major on this too much. As I said, we used to have small, medium and large biomass, Tier 1 and Tier 2, and a tier threshold of 15% of its maximum theoretical capacity. We're changing that to one set of rates across the board, and if you notice, those rates are higher than the large biomass tariffs used to be, which is one of the things that the government want to change in their support of biomass. They feel that the best way to support biomass technologies is to support ever bigger boilers. They don't believe that small distributed generating boilers, you know, the 50, 60 kilowatt mark boiler, or even the 500 to 600 kilowatt size boilers, is an effective way of promoting biomass. What they'd really like to do is really big industrial users of heat to suddenly take up biomass in multi-megawatt systems, 10 to 30 megawatt boilers. And they'll be very happy if they only had 5 of those in a year that are accredited, because that would make a great deal of impact on their efficiency targets, on their renewable targets, but actually it would mean that they'd have very little projects to administer. At the moment, there are something like about 20,000 renewable heat incentive projects on the scheme. 99% of them are biomass boilers. And that's just on the non-domestic scheme. On the domestic scheme, there's another 12,000, and they're mostly also biomass boilers too. So far away, runaway success in the renewable heat incentive, but the move is to ever bigger boiler plants, incentivize them, fewer projects, but bigger impact. As you can see, the tier threshold has gone up. With ever bigger boilers, they tend to be running ever longer hours. So the tier threshold has gone up to 35%. And what that really means is if you take the energy that would be produced by a set boiler size for 8,000 hours a year, then that will be its maximum capacity. But actually, they're prepared to pay you tier 1 at 35% of that energy content. So a megawatt boiler would have a tier 1 allowance, if you want to call it an allowance, of 3 million kilowatt hours. After that, it would drop down to tier 2. At the moment, that's around 1.3 million kilowatt hours. Tariff guarantees. So yes, you can lock into a tariff. This is quite a fundamental change. So you go through a preliminary accreditation process, you apply to the RHI and say, this is what I'm going to do, is what I'm going to be doing acceptable? They come back with a stamp and say, yes, we will pay you if you get on and do this project. And that's as far as it's gone. Now we're going to move that one stage further to say that if you need it for projects that are very capital heavy, then we will allow you to apply to have your tariff locked in, so that you've got a little bit of security when you've got to go to your finance house, or the rate will be there when you come to making your project happen. The technologies that get that, it is biomass boilers, but greater than 1 megawatt. I think the feeling is that the sub 1 megawatt market's been quite happy existing without tariff guarantees for the last 5 years. Why does it need tariff guarantees now? But the bigger biomass projects haven't happened, and maybe tariff guarantees has been a barrier to that. So tariff guarantees is something for large biomass. Also geothermal projects. I know there was looking at geothermal in and around Offanem, and one of the things that the growers around there wanted was, is this going to happen? And if it does happen, are we going to get paid? So geothermal is one, and I know there's quite a lot of moves to keeping that supported. Biogas, AD plants, ground source heat pumps greater than only 100 kilowatts, would you believe? Ground source heat pumps at 100 kilowatt size, they don't actually look particularly big or expensive, but actually they haven't really been taken up as much as the government would like. So maybe they're trying to remove a barrier to these projects by putting a tariff guarantee in place. And also for solid biomass combined unit power, where the projects are ever more complicated. You've suddenly got an interaction with electricity that you hadn't got before. You've got to put a generator in, and you've probably got to put a slightly bigger boiler with slightly higher temperatures that's going to be more expensive. So a tariff guarantee process could work quite nicely for that. One of the principles behind that is, yes, you can say your commissioning date will be whatever you like. However, you need to be commissioned within the 6 months of that date. So otherwise you lose your tariff guarantee, you lose your tariff, you've just got to apply like anyone else, and there may be no scheme to apply to. So you've got to commission within 6 months of your stated date. You've got to provide all sorts of business security and proof that the directors are going to sign off the project, and we're close to financial close, and all those sorts of rules around making sure this project is actually going to happen. The thing with tariff guarantees is when it comes to looking at how much budget is going to be allocated, they count towards budget allocation, even though they have not happened and no money has been paid out yet. So they want to make sure that these projects are actually going to happen. Otherwise, you're reserving budget that maybe someone else could have used more usefully, especially if you end up not doing your project at all. And of course, the end of the scheme, 31st of December 2019, if you've not got commissioned by then, there's no scheme to apply to, regardless of whether you've got a tariff guarantee or not. They can be taken away from you if you decide that actually your project looks completely different. And when you go to apply, they say, oh, well, actually, that's not what you said you were going to do, and therefore your tariff guarantee doesn't apply any longer, or if you've misled them. Do you need planning permission? No, at the moment you don't, and you haven't done since 2011. However, the only section about planning permission is that sentence there, those 3 lines. But it's quite a big change. So going forward, you will need planning permission for your renewable heat incentive project, or the ability to prove that you didn't need it. And that could have quite a big impact on the speed at which projects get put together. So if you've got a friendly planning consultant, it would be worthwhile talking to them at the outset. Or just making a planning application regardless. I know that planning authorities and businesses aren't the friendliest to people quite a lot of the time. But if you don't get it, if you don't have that piece of paper that says that you don't need it, or here's your planning permission, then you will not meet the criteria of the RHI scheme. You will not get your incentive. So don't forget about planning permission, whatever you do. Don't plough on regardless. And if you go for retrospective, then you'll have done your project, you'll be burning fuel in it before you even can even apply. Biomass combined heat and power, so that's putting fuel into a big boiler, making heat, turning that heat into electricity. That's always been something that's been supported under the renewable heat incentive. Up until August last year, you could put in as small a generator as you like, as big a boiler as you like, and that would constitute a biomass combined heat and power system, and you'd get an inflated rate around 4 pence, 4.2 pence a kilowatt hour. And compared to large biomass at 2 pence, that's quite an attractive thing to do. There was a bit of a mad panic in the Department for Energy, as it was then, DEC, and then latterly the Department for Business, who adopted Department for Energy, about that's over-supporting technologies where the combined heat and power rules were being used to get big boilers when really they weren't actually making very much electricity. So they thought it was a ruse and something they wanted to close down. So they set some emergency legislation that said 20% target, you must have 20% electrical generation capacity compared to your biomass boiler thermal input. Otherwise, you won't get the full rate, and the rates will decrease proportionally. There's a big hoo-ha around that, especially where projects were already committed. People have spent quite a lot of money already getting these projects to a certain point, no tariff guarantees, no guarantee that they get a rate, and suddenly we bring in a major change that means you're going to cut 50% off your project's bottom line. And a subsequent change of heart by the government in January this year, or when they had a change of heart in September, but January was when it became effective, was to reduce that to 10%. And who knows what it's going to be in the new regulations? Because, as I say, I think that's the reason they pull the regulations at the moment. It could be 10%. I know the government's plan is to keep it at 10% with the potential to move it back up to 20% in time. Hopefully that won't put projects off, and as biomass combined heat and power is available for tariff guarantees, then I would advise anyone looking at a biomass combined heat and power project at the back of today, or even already thinking about one, to go for a preliminary accreditation and tariff guarantees to make sure that their project is going to receive the incentive they want it to. As I say, the rates reduce proportionally when a target isn't hit, so when you don't hit 20%, and it's more on energy than it is on than actual capacities, rather than on power. And so if the target was 20%, you only hit 10%, then you will get half of your energy paid at the 4 pence, and you get the other half paid at the biomass boiler tariff. Hopefully you're going to cover a little bit about that, Ollie. If not, then we might have to revisit it in a session. Heat pumps haven't before been allowed to have preliminary accreditation. Again, maybe that was a barrier to their uptake. So they're bringing in that, and also tariff guarantees. The rates are unchanged for heat pumps. There's still a tiering threshold of 15%, and the rates are something like 8 pence a kilowatt hour at tier 1. So still quite attractive in terms of the support levels. For some people, using shared ground loops, so if you've already got a ground loop that's only being used by someone at a certain point of time, maybe you want to use that ground loop rather than putting in one yourself. Under the old rules, you had to put your own ground loop in, otherwise it wasn't considered a complete scheme. Now you can share a ground loop. And you can also free up other heat sources. So if you're going to put some heat, other forms of solar energy stored in the ground. I'm not quite sure what other forms of solar energy are, but those are the words in the regulations, would you believe? I thought it was just the sun, but hey, there we go. But you can take space or process cooling and use that as a source for your heat pump. And other processes where the primary process is not to generate heat. Well, if you're making heat, then your primary process is to make heat, isn't it? So again, I'm not sure that's a particularly enforceable sentence, but hey, I didn't write the words. Digression, made up word, but basically it means if things are too popular, then we'll reduce the rates. I'm going to bring that graph up again in a minute, but it's a means of making sure the scheme remains cost effective, so we're not over-supporting things. And we've seen it in the small biomass, massive uptake in small biomass, and the rates have come down 5%, 10%, quarter by quarter for about the last 3 or 4 years, to the point at which they're lower than the medium biomass rate, which is a bit balmy. So they're making changes to that to make it more appropriate, so that actually the digression mechanism isn't quite such a sledgehammer to crack the proverbial nut. As you can see, this is the graph of uptake, and this is for medium biomass. This is quarter by quarter, it might even be month by month, but yeah, it's month by month, sorry. The number of projects that are in the in the RHI scheme for medium biomass. Blue is actually schemes that are up and running. Red is ones that haven't yet had any money, and yellow is ones that they think are going to come on stream, subject to them meeting all the eligibility criteria. And so if the columns hit one of either the purple line or the blue line, then they're at risk of digression. And if they hit the blue line, they certainly will have their rate reduced. And so, as you can see, there was a massive uptake of medium biomass boilers in March and April this year. We've only got the March figure there because the April figure hasn't been published yet. We'll have that in a day or so, probably by the end of this week. But actually, it's going to hit that blue line. And when it hits that blue line, the rate will come down. And so there is going to be at least a 5%, if not a 10% reduction in the current scheme medium biomass rules. Now, if the new regulations were in place, then all of this will be thrown away and we're back to 2.96 and 2.08 pence a kilowatt hour. But until those rules have been made law, then we are going to have a reduction in medium biomass. So if anyone is considering getting a short-term project in between now and whenever the regs come in, just be aware that the rates aren't going to be 5 pence for very much longer. And that that digression will hit on the 1st of July when that happens. The budget cap, so this was something that, I say, was promoted in the reforms, but actually came in immediately. It was part of the reform package, but it came in a year ago. And we can close the scheme, or members of Parliament can close the scheme at 21 days' notice, a minimum of 21 days' notice, if we hit the forecast expenditure. So if the whole scheme is going to go over budget, that's it, 21 days. Any schemes that aren't applied for in that 21-day period will not be able to get any renewable heat incentive until it gets reopened with a new budget allocation. Nowhere near close enough at the moment to be concerning. There's a graph in the next slide. There we go. Oh, there was a graph in the next slide. Don't know what happened to that. Yeah, currently not close enough to be concerning, and there's an increase in budget year on year. And so by the time we get to the end of 2021, there's 1.1 billion in that budget. So we've been running underneath that budget by about 50 to 60 million at the moment. So we're not worried that we're going to hit that budget cap yet. So sorry about that graph. I'll make sure it's in the slides when they get uploaded to the web. And there's a whole suite of other changes. Way too numerous to mention. I've put up the highlights in there. Highlights, lowlights, whatever you want to call them. I've put them all in there. Make sure your consultant reads the rules. I think I would say that. I'm a consultant. I get paid to read rules. But make sure you or your consultant read the rules. Make sure you understand what the changes are and how they might affect you. Because just because it was fine last year does not mean it's going to be fine going forward. So when is this all going to come in place? What I'd like to do, we'll find a little basket before the end of the morning session. If you've all got a business card or a bit of paper, write your name and the telephone number down on a bit of paper. We'll have a bit of a guess as to when this is going to be. And EBTEC have very kindly put up a prize of a bottle of champagne to the winner. These rules, these regulations, they are not in Parliament at the moment. They were meant to be back in Parliament. There's a 6 to 8 week process to go through once they are laid into Parliament, and we've got a general election on the 8th of June. So, a bit of a guess when you think these rules are going to come into play. And I'm not going to tell you when I think it is, because that might give you a massive benefit, or it might be completely false. But I'll stick a basket round and stick your name and number and your guess, the date they're coming through, and we'll publish the results when we know when the date is. So absolutely no idea. I'm going to say by the end of the year. I'm not going to tell you when by the end of the year, but I'm going to say by the end of the year. And I know some people in the office think it's going to be April next year, but I think that's too far ahead. So a bit of a boundary for you there. Great. I'm going to take the opportunity to hand over to Ollie. He's going to talk about heat pumps. Any questions, then you can either jot them up on the board if you think we're not going to cover them, or we'll answer them there and then. Any questions from what I've said so far?
The pre-accreditation, John, presumably that isn't available now.
Preliminary accreditation, yes, it is available. Preliminary accreditation is still available.
Now available, but not with the guarantees.
Not with the tariff guarantees. No, tariff guarantees aren't made law until the new regs come in.
John referenced CHP market, sorry. Why are payments taking nine months for the RHI?
Once you go from application through to approval, a number of reasons. They don't have the team. They don't have the experience in biomass CHP. They've massively upscaled in Ofgem to look at biomass projects, and the people that can actually understand and get their head around biomass combined heat and power are few and far between. Those people have actually mostly sort of working in AD section at the moment, and that's massively overburdened with the number of projects that there are in that. And then there's the complexity around the rules, making sure that projects do meet the requirements and the regulations, especially seeing as there's people want to make sure, or rather Ofgem wants to make sure that these projects aren't going to be seen to be over-supported. So they're making sure they adhere absolutely by the rules. And of course, then any projects that were applied for pre-August, before these changes, then there's a risk that those projects would actually complete when they were applied for, and people were just trying to pull a fast one and get a project into the system, and they're going through those with even finer a tooth comb than they going through normal projects. So they're taking even longer to make sure that, and they have the ability to do pre-accreditation audits, and one of my projects has had a pre-accreditation audit, and I think many others who are applied for before August will do so as well, and that adds another 3 months in the middle. Does that answer your question? Yeah. Yep.
Okay. Hi everyone. Good to see some friendly faces in the crowd and some faces that I haven't seen before. As John mentioned, I'm going to be talking about heat pumps. I'm also going to be doing a bit on biomass CHP a bit later. The idea being just to give you a general sort of overview of what a heat pump is, how it works, and how the RHI interacts with a heat pump. So briefly, heating accounts for typically 90% of energy use in the horticulture sector. Beyond energy saving measures like climate control, thermal screens and venting regimes, what else can you do to reduce the cost of heating? Well, another method would be to buy a bit smarter. However, you're still at the mercy of the energy markets. Ideally, you'd be implementing energy saving measures, purchasing energy at a better price, and of course there is the possibility of changing your heat source. If you've got an old boiler running inefficiently and there are other heat sources available which garner some RHI payments, it's certainly worth looking into. So heat pumps are supported by the RHI, meaning that you get an income for every kilowatt hour of heat that you produce. These are the current rates for water and ground source heat pumps. As you see, they've got a tiered system similar to the biomass rates, and air source heat pumps are paid a single flat rate. So what is a heat pump? The dictionary definition is a device that transfers heat from a colder area to a hotter area using mechanical energy. So we've all got one in our homes in the form of a fridge. Effectively, a heat pump runs on a refrigeration cycle. So just looking at that in a bit more detail. Heat pumps generally take heat from a low-grade source, which could be the earth, it could be a water source, or it could be the air, and boost it to a higher temperature to make it usable for heating. So if we were to take the top left corner of that diagram, we've got our liquid vapor mix of refrigerant. That is passed through a low-grade heat source like the earth. That evaporates effectively the mix of liquid and vapor. We can then compress that, leading it to a higher pressure, higher temperature vapor. And with that vapor, we can heat an end heat use, such as a greenhouse. Once that vapor's been cooled, it condenses. We can then pass that through an expansion valve, leading it to low pressure again. and that reduces the temperature, and we can repeat the cycle. So what are the variants? Well, yeah, as I mentioned, it depends on what source of low-grade heat you've got. There's obviously ground source, which could be laid flat along the ground, probably about a metre under the earth. Alternatively, you could use a borehole for ground source heating. Water source, if you're lucky enough to live next to a lake. Alternatively, you could be on top of an aquifer. That's another means of using a water source heat pump. And air source, which you often see tacked to the side of a building. Doesn't look particularly pretty, but it works. Ground source, I mean, the temperatures you're looking at recovering from the ground anywhere from about 8 to 12 degrees. Water source, again, you're probably looking at about 4 to 10 degrees. An air source, which is a bit more variable, it could be anywhere from sort of minus 15 degrees to 30 degrees, depending on the weather. So here are a couple of examples of a ground source heat pump. The one on the left is, as I mentioned, the flat coil type, buried about a metre and a half underground. Obviously, you need a significant amount of land to be able to utilise that system. It's often put in people's back gardens, that sort of thing. The alternative to that, where you haven't got space to lay out loads of coils, is the borehole. Here you can see a pipe. I think that's actually the drill, but effectively you'd have the refrigerant piped down into the borehole. They would put some thermal grout around it, and effectively, yeah, you could run the system that way. Water source heat pumps, they can be installed next to any water course, such as a canal or a lake, or as I mentioned, if you are above an aquifer, you can extract water that way, extract the heat from it, and then pump it back down into the aquifer. That's what these examples are here, primarily, and you can see there from the size of the heat exchanger stood next to one of our colleagues, the sort of size systems that you're looking at, and the kind of plant room that you may need to operate on a large greenhouse. Air source, as I said, can typically be found on the side of a building. This one was used to heat and cool a greenhouse. One important note about that and the RHI is that an air source heat pump that can cool and heat is not eligible for the RHI. So if you are intending to claim RHI on an air source heat pump, it needs to be heating only. You're allowed to install a ground source or water source heat pump that can run both ways, so cooling and heating, but you will only get paid RHI on the heating. So probably one of the most important figures for a heat pump is the coefficient of performance, or COP. It is effectively the total energy output in heat terms over the electrical input. So electrical heater, for example, you put in 1 kilowatt hour of electricity, you get about 1 kilowatt hour of heat out, or you do get 1 kilowatt hour of heat out. For a ground source heat pump, you're looking at a COP of about 4.5. I put seasonal there because it varies depending on the weather. Less so for ground and water source, but certainly for air source. Water source there, as you can see, a COP of about 5.5, and air source 3.5. And a heat pump will normally produce hot water, if that's what you're covering, at about 55 degrees C. So on to the RHI criteria. As I said, the key one for RHI is COP. Your heat pump needs a minimum of 2.9 coefficient of performance. The installation needs to be completed and commissioned after July 2009, so there shouldn't be any danger if you're considering a new project. No grants or funds can be received for the installation. That's not to say that any pipework connected at the back end can't receive a grant. It's mostly for the integral equipment, so i.e. the heat pump, the ground source loop, for example. The plant must be new, and it must be providing heat for an eligible purpose, so heating a building, heating water, or carrying out a process within a building. The final criteria for the RHI are that the metering arrangements are correct. So just moving on to that briefly, you're going to need at least one MID compliant heat meter. It comprises of a flow meter, temperature sensors, and a calculator to calculate how much heat you are producing. You may need more if you've got fossil fuel boilers on your system or other biomass systems, for example. And you may need more heat meters if your heat losses are particularly high. So just running through a quick example of a water source heat pump. We're looking at a heat demand of 1 megawatt for a 1.5 hectare nursery here. You would use about 400,000 kilowatt hours of electricity, which would produce somewhere in the region of 2.2 million kilowatt hours of heat. Obviously, you've got the electricity cost to factor in. You would get your tier 1 and tier 2 RHI to a certain extent, as well as a gas saving. So by producing this 55-degree heat, for example, for grow pipes or for preheat for boiler, you are making a gas saving. Your net income is just over £150,000, so a payback of 2.57 years for a water source heat pump. Now, ground source heat pump, considerably more expensive, and why would you choose one when you can do a water source heat pump? Well, not everyone, unfortunately, has a lake or an aquifer underneath them, so they will need to install a ground source heat pump. As I said, the costs are significantly more expensive. The COP is slightly worse, so you'll be using more electricity to produce the same heat. And you can see there a net income of just under £150,000. So a payback of 5.75 years there. That's just to give you a brief overview of what a heat pump is and a couple of examples. Does anyone have any questions?
Is it possible to configure it so that you're taking advantage of the cooling side of the heat pump as well?
You can do for, as I said, for ground source and water source, you can take advantage of the cooling. You won't get paid RHI for it.
Yeah, I don't mean using heating at one time of the year and cooling at another time.
Right.
Using heating and cooling simultaneously.
No, you wouldn't be able to do that. Because it's a refrigeration cycle, you'd either be running one way or the other. So it would have to be either cooling or heating. I'm not sure if there are any technologies out there that you could do it simultaneously.
If you're planning a new glass house, would it pay to put the coils in the ground before you build? Or do you lose that gain?
That is a problem. Depending on the depth, if you're only putting the coils in a meter and a half under, what you're effectively doing is cooling the soil. So you end up with a net outcome that you're not actually putting any heat into the greenhouse.
If you're using an aquifer, do you have to return the water to the aquifer to make a complete cycle?
You do, yeah. So
It must be the in and out.
Environment Agency are pretty strict on abstraction from aquifers, I think.
How about from the licensed water?
You could, you'd have to put the water somewhere. If you've got an abstraction license of, I don't know how many meters cubed per year, it's possible. Okay. I think I'm passing over to Simon now, who's going to talk you through heat pumps no, not Simon, sorry, Martin. So, he's going to talk you through heat pumps in a bit more detail and some of the projects they've done in the UK.
First of all, thank you for the invitation from the people of GrowSave for us to give this short presentation here today. My name is Martin Veenstra. I work for a company called Surfund in the Netherlands, and after a few slides of just explaining a little bit what we do in everyday life, I'll show you some practical examples of the application of heat pumps in horticulture, at least in the projects that we do. So a few quick things about ourselves. We're a company based in the Netherlands. We've been around for approximately 120 years, about 100 people in the nice small town of Poeldijk in the westland area of the Netherlands, close to The Hague. And basically we're a greenhouse builder and installations company. So we've got basically all the disciplines for building, heating, cooling, electrical engineering, lighting and irrigation technologies in-house. And we work worldwide and also, of course, a lot in the UK right here. Just a quick overview of some of the countries we've been active in so far. Here in the UK, we work a lot with a company called CMW, one of our partners here, and we partner up with quite a few companies in the UK as well for all the different aspects of the greenhouses that we build. I won't bore you too much with something that's standard on every slide nowadays. Our company vision is to basically build projects with our clients for producing healthy, clean and safe food on a year-round basis, and not only in greenhouses but also in other types of structures, as I'll just briefly touch on to give you an idea of where we apply these heat pump technologies. So I'll just skip this one just very quickly. This is just an overview of the turnkey approach that we have to our projects, where we basically take off from basically the business case side right up until the project execution and project commissioning and everything that falls in between in order to make a successful and basically profitable project. And dealing with questions of how to work with energy in the most efficient way possible is of course a very important aspect of that. And as we'll see, heating and cooling is a very important part of that. So one of the projects I'll be discussing a bit more in detail a little bit later on is Red Roof Nurseries in Cottingham, 1.6 hectares of tomatoes, and they're using heat pump system, ground source heat pump for heating their greenhouse. One of the ways they're heating it, but that's an important part of it. So I'll be coming back to that project in more detail a little bit later on. Some other examples are, for example, Spring Hill Nurseries in Evesham, Sandylands in Evesham. We do more than just heat pumps. We also did the LED lighting system for this project, for example, which is a completely different topic on its own. Maybe in the coffee break we'll have time to talk about that. Another project using waste heat, but not using a heat pump, is a project in France called Jardin de Rabelais. They're using full LED lighting as an artificial lighting source for their crops, and they're getting waste heat from a nearby power plant. I think you can easily see it from the greenhouse, so they're also making efficient use. Another type of project where we're seeing more and more the application of energy efficient heat sources are, for example, the new and upcoming market of vertical systems, which are basically intended to save on energy for heating and cooling a lot. For example, at an orchid greenhouse, this example is a three-layer setup fully automated, about 3,000 square meters, so that's just a little less than an acre, but primarily for reducing the cultivation phase. We've got some more extreme examples, like a vertical application in the Netherlands for propagating lettuce plants efficiently. That requires a lot of cooling power and also a lot of heating, and both are performed by a ground-sourced heat pump. But again, it's a little bit outside of the scope of this particular meeting, so I won't touch on that too much here. And the same goes for new upcoming indoor growing applications, like for a large food processor in the Netherlands, where we will have this similar vertical farming approach with LED lighting and also a heat pump cooling system. And who knows what next? we ourselves are doing experiments in indoor rooms with only artificial lighting to grow cherry tomatoes quite successfully. This is looking far away into the future, but this will require a very energy efficient solution, and one of the good guesses is that it will probably heat pump based because it is potentially so efficient. So, but this is still a few years ahead, I guess. So, someone had the same idea as I do. I think great minds think alike. I hope to think about talking about a refrigerator. So probably I had a moment to think about it already, and I have this question a lot when talking to people about heat pumps. So what happens when you open the door of your refrigerator in your kitchen? Now I dare to ask for a show of hands. What happens to the temperature in your kitchen when you open the refrigerator? Does it go down? Any hands? Does it go up? Two persons, three, yes, or no opinion. Well, the natural response, as always, is to say, well, you open the refrigerator, so all that cold is coming right at you into the kitchen. But actually, as Ollie already pointed out in the earlier, you need something to get, for example, that cooling power. So it's transporting energy from, let's say, from one place to the other by using some means of mechanical energy. So when you are producing cold, you know, the law of conservation of energy says you have to have heat somewhere else. And in the case of a fridge, that's at the back of the refrigerator. So while initially it might give this nice cold feeling, in essence, you're just heating up your whole kitchen. And you will find that actually the heating will be a bit more in energy terms than the cooling power that you're getting in effect. So now when you get this, when you're in a pub quiz and this gets asked, then you know that actually it will get heated up. Okay, the previous speaker did a great job in explaining the process, so I can hopefully skip over this. The heat pump I'm showing here is a slightly bit bigger than the ones shown in the previous slide, but the working principle is exactly the same. Now, there are a lot of different terms, and I won't go over all the acronyms, but these are just some of the ones that we come across a lot. We've got the COP, the coefficient of performance, often related to the heating capacity of a heat pump. The energy efficiency ratio, typically used a bit more when talking about the cooling capacity, or air conditioning, or cooling capacity of heat pumps. And then is a whole range of the SPF, the ESSEER, depending just on what type of regulation or what type of standard is being used to evaluate the efficiency of the heat pump. So in the latter example, for example, this is used a bit more where you have to adhere to European standards, where they perform some sort of seasonal weighing to the efficiency of the system, depending on let's say the operating conditions, while still maintaining a certain output of cooling. So this is more related to cooling. So I'm happy to say that there is within GrowSave a good comprehensive overview of all the rules and regulations, because it can be a forest that can be quite daunting to get in and also to get out again. So for purposes of making this easy, I'll just talk about the COP as a measure for the efficiency, which is exactly the same as the previous speaker already explained. So we deal mostly within, well, speaking for our part of the business, we deal mostly with ground source heat pumps, where we have an open system, so an aquifer-based system. This is quite typical for us because the capacities for heating and cooling that we come across in our types of projects typically start at around 500 kilowatts of either heating or cooling capacity required, typically even a bit higher. And most of the projects that we've worked on so far have been based on the ground source heat pumps using aquifers as either low-grade heat or cooling source, but I'll get back to that in a little bit. And a lot of the things that we have to look at, or the clients have to look at, or you as a potential project planner have to look at, are a lot of rules and regulations. The ones that we come across have a lot to do with first a good assessment of the soil that you have, often down to a depth of 150 or 200 meters, because that's typically how deep the boreholes will go for an open loop system. And there was a whole process leading up to that assessment, including assessment of the soil, the hydrological properties. If you're talking about aquifers, what is the flow speed of the groundwater in the aquifer? What are the chemical composition of the soil? If there was a lot of iron, there are chances of oxidizing pumps and metal parts, etc. So there was usually quite a long journey ending up before you end up at a good assessment if the location that you've picked for your ground source heat pump project is actually suitable to run the system efficiently. And it often involves making some, let's call some experimental boreholes to get a feeling for the capacity of water that the aquifer will be able to give you in your system. I won't go into this too much because the people at GrowSave and the people from FEC have much more experience with all the local rules and regulations that apply here. But typically, we come across two things that I'll just mention. One, yes, because of the volumes of water that will be transporting around in the entire system, typically you have to put back all the water you take out of the aquifer, because we're talking about many cubic meters of water that can range between 50 and 100 cubic meters per hour, depending on the capacity of your heat pump. So if you have to store all that water somewhere or buffer it, that will mean a lot of space for water buffering. So typically the regulations say that you have to put everything back. A second consideration, and that relates a bit to the question that the gentleman asked about cooling as well with the heat pump, is that when you want to do that, then if you're generating cooling power, then you are also generating heat at the same time, as we just saw. And there are quite particular rules typically about putting back hot water into the aquifer. In Holland, there are very strict regulations on at what temperatures you can inject water into the aquifer for returning the water. It can range anywhere between 15 and 20 degrees Celsius. So those are very important things to look at. And then the second thing related to that is that if you are storing hot water in one borehole and cold water in one borehole, then there are typically rules about what, let's say, the thermal imbalance or the energy imbalance may be over a certain amount of time. So there are quite some things to look at when doing this. This was covered already. Typically what we do, like I said, we use a setup like on the right-hand side, where we're actually using water from aquifers to create the loop, basically, typically consisting of a warm well and a cold well, or a number of wells which constitute the cold side and a number of wells which combined constitute, let's say, the warm side. And how many wells typically depends on the water capacity and the flow capacity that the aquifer is able to give you. Here's just a typical layout of a greenhouse where we have the warm wells and the cold wells situated, typically spaced apart. Where they are exactly located and how much space is in between depends on basically the results of that hydrological study that has to be done beforehand, especially if you want to do sort of a seasonal energy storage, which I'll touch on a little bit later on. I'll let you see why. No, let's go back one. Yeah. So you can imagine if you're putting a lot of cold energy or cold water in an aquifer on the top left side and a lot of warmer water in the bottom right side, if you don't keep track of the balance between the two, you get a sort of a thermal shortcut on the long term. So that means basically that the part of the aquifer where it's warm, water will start siphoning to the cold air, to the cold part, and start heating up the cold water. And that means if you're also using your heat pump system for cooling applications during the summer, for example, it means you're effectively raising the temperature of your groundwater, which will have a negative effect on the cooling capacity. But I'll come back to that in one or two slides. Just a little bit about the borehole. We've seen a picture similar to this from the previous speaker. What we're doing here is just showing just sort of a typical composition from let's say a borehole study where people take a sample. So the actual composition of the aquifer is quite important. Is it gravel? Is it fine sand? Is it coarse sand? And then of course there is an evaluation of the amount of water available in the aquifer for using as the ground source. And actually, typically there will be, let's say, a blind. I don't think the pointer's really working, but let's say in the middle, the yellowish section is, let's say, the borehole, and the blue area is actually a sort of a filter structure which allows the groundwater to fill up the borehole and allows it to reach the pump, which will be used to extract water from the borehole and transport it to the heat exchanger of the heat pump. So, I thought I'd give you a little bit of a shock on this morning. A lot of nice lines, but this is actually a sort of typical schematic for a heat pump setup where, and I wanted to show you an example not just for the heating application, but an application where we can also use the heat pump installation for cooling as well. So just very basically what we've got here a number of wells. Let's call these are the cold wells and these are the warm wells. And what we're basically doing is running the well water through the heat exchanger, and by doing so, supplying the evaporator of the heat pump. Now, what's happening here is that the evaporator of the heat pump is connected to a cold storage tank, and the condenser is connected to let's call it a low-grade heat storage tank. So, and typically what we are running these systems at is that the cold tank is filled up with water of a temperature between 5 and 7 degrees Celsius typically, and the low-grade heat storage is in the range that Ollie already mentioned. That's basically in the 45 to 55 degree range. So actually we're using, let's say, both the heat produced and both the cold produced. And what we're doing in a seasonal system here is that in the summertime, when we are producing a lot of cooling power using the heat pump, we are at the same time using a little bit of heat for, let's say, processes in the greenhouse operation that require heating still, for example, for dehumidification or reheating, etc. But we also have the possibility to use what we call a surplus heat exchanger and to directly charge that surplus heat, or some of it at least, up to the level that is allowed, let's say, in the permit for loading, the loading temperatures to inject back in the ground. We can actually fill up those hot wells with water which is a bit warmer than what the natural groundwater temperature would be. In Holland it's also the same. It's between 10, 11 degrees. So depending on the permit, that can be anywhere between 15 and 20 degrees Celsius. So that's what we're doing in the summertime when we are actually producing cold or cooling power with the heat pump. Now, you can imagine that in the winter time, we're doing the reverse. So we've got a reversal system here for changing the flow from, let's say, from cold to warm, back from warm to cold. So then we're extracting the water stored during the summertime, and we're upgrading it using the heat pump. And the advantage here is that we're quite a bit above the typical ground bottle level. So we can then quite efficiently upgrade that to a higher temperature and use that in the greenhouse. So in applications like that, we take advantage of both the cooling and the heating capacity of the heat pump, because we can reverse the direction of the flow from the wells. Now, another advantage of this is if we're storing 5-degree water, it means that in the summertime, what we can also do is use something called free cooling. Well, almost free cooling. There's no such thing as a free lunch, but we're getting close here. So what we're doing then is we're actually depending on the amount of energy that has been stored during the summertime, so when we had a lot of residual cold that had been stored in the ground, so we basically got a bubble of water in the ground which has a temperature in the range between 5 and 7 degrees. So what we then do is make the flow from the cold wells to the warm wells again, and through the heat exchanger we can actually bypass, depending on the capacity required in the greenhouse, we can bypass the heat pump altogether and get the cooling power from the ground and directly enter it into the greenhouse through the cold storage tank. So that is an additional sort of bonus that you can get if you have the opportunity to really store the residual cold that you are generating during the summer. Now the trick here is, as I mentioned before, is that on the long term, I think in the Netherlands the regulations state that it has to be within 20 years, let's say the net thermal balance that you get from season to season over a year should be practically zero. So you have to be careful in these kinds of applications that you, the amount of heat that you put in during during the summer needs to be offset almost precisely by the amount of cooling power you extract from the ground during the summertime. So that's quite a tricky business, but and it's not for all types of crops, but we use it a lot in potted plants and orchid production, for example, which have very rigid cooling regimes during their production cycle. Metering was already mentioned before, so you have to have a very careful control of the entire system, because as you saw already in the pictures, and I saw that GrowSave made a very nice technical handout in 2 parts for the heat pumps, giving you a little bit of overviews of what the investment costs are in especially the open loop systems. An investment of that scale you want to take care of very well. So metering the entire system is very important, and that's what we put a lot of focus on when we design and build these systems, because a typical example is if you don't treat the wells gently, water pressure in those wells are quite important. If you don't monitor and control that correctly, you have the chance of effectively blowing up a well, rendering it useless. So metering, monitoring is of vital importance of using these ground source systems. It's a little less critical in the closed loop systems, but especially when you're thinking about using aquifer-based systems, please take care that you have a good metering and monitoring system and safeguarding system to prolong the lifetime of those wells and keep them running at optimum efficiency. Just a couple of examples. The one I showed before is for a 7.5 hectare orchid nursery, and they require 18 degrees for a certain amount of months, even when it's 35 degrees outside. So there you can see the benefits of having a combined heating and cooling option in your heat pump installation, and especially also the free cooling option in the summertime when you have that large amount of, let's say, cooling energy stored in the aquifer. Also other applications, this is a combined application where we have 3,000 square meters of greenhouse and 3,500 square meters of plant growth rooms, which we both built for a company called Rijkswaan in the Netherlands. They are a seed producer and a breeding company. Heat pumps are great also if you have the cooling, if you need cooling power and you can do something with the residual heat. For example, here a large part of the greenhouse is fitted with floor heating, and also the offices connected to the facility the floors are heated using residual heat coming from the heat pump system. So these are great opportunities to really get the most out of the electricity you're putting into your heat pump system. And of course, I've got an example here from Red Roof's nurseries in Cottingham, which I hinted to a little bit earlier. Here we're not doing they are not doing a seasonal storage of energy, but they are using the ground as a low-grade heat source. So again, we've got about 2 wells which are designated as the hot wells for abstraction, and they've got one well for injection. So, and the total combined flow is around 80 cubic meters per hour. So that's the total flow. That flow is going through a heat exchanger, and again, that's feeding this line shouldn't be there. That's going to the heat pump. And before it goes to the greenhouse, they're using it, and actually the heating inside the greenhouse is more the expertise of my colleague Andre, who is also here, but they're using the tube rail heating system, so that's a relatively low temperature heating system. So they're feeding that into that system by using a sort of a 0 point or buffer control tank in between. Now, in this particular situation, the temperatures coming from the ground are around 11 degrees Celsius, and it's being put back at around 5 degrees C again. And in this particular case, there is quite a large groundwater flow speed. So all the water going into the ground at a certain temperature is effectively gone quite quickly. So you don't have the problem of heating up or cooling down effectively the aquifers that you are abstracting from and injecting back into. Because we wanted to show some practical examples. Oh, here we go. It's basically the same situation, but again, based on the schematic before. So we are abstracting from at 11 degrees and injecting again at around 5 degrees Celsius. So metering is important, as was already mentioned, to comply to all the regulations from the RHI. So from the system, it's very easy to get, for example, the running hours of the heat pump at any given time. So this was in operation commencing around mid-July 2015, and I took here up until beginning of May of this year. So this is the accumulation of operating hours over the course of just a little under a year. Something else that we'll show, and this is a bit of a mess, but I wanted to do it anyway. I picked a relatively cold month. This is this is February of this year, starting February 1st, ending March 1st. And here are some of the condenser temperatures. So the temperatures basically coming from the heat pump and going to the tank and further on into the greenhouse. And we always aim that you're around this 50, between 45 and 55 mark. Occasionally going up to the upper limit of 60, but above 60, it's not really. You're not adding anything to the efficiency. Actually, in these systems, what we're trying to do is to closely match, let's say, the water temperature generated by the heat pump, to keep that relatively close to the return water coming back from the greenhouse. And based on the calculation of the climate computer inside the greenhouse about the heating capacity required, our system then calculates the most efficient way to run the heat pump in order to meet the heating demand, but not waste any heat. So what we don't do is say, okay, the heat pump can generate water of 50 or 55 degrees. We'll do that, send it into the greenhouse, and let's see what happens. Now we're actually looking at the returns coming from the greenhouse, combined with the calculated heating capacity required, is to run the heat pump at a level that is efficient. And here, what I plotted here at the bottom is the temperature difference between let's say the fluid or the water temperature coming from the condenser of the heat pump and coming back. So it's quite nicely going up and about the 5 degree mark. Another important part, and excuse my voice because I've been traveling a lot in too many badly air-conditioned hotel rooms the last week, so my cold is acting up a little bit. What we're looking at a lot is running efficiently. So what we see here is an actual measurement of the total electrical consumption, which is indicated by the red line on the right-hand axis, and the heating power generated by the heat pump which is plotted in the blue line and the left-hand axis. Now this is a little bit noisy, but if we then, and the system does this automatically, also calculates the COP. Of course, it goes down, up and down a little bit, but it's averaging out quite nicely around that 5 at the 5 mark. So that means that, as was mentioned, that for every kilowatt of electricity that's put into the system, we're getting back about 5 kilowatts of thermal heating power, which is quite nice. Oh. A few final thoughts to recap is, ground source heat pumps can be very efficient, but what is even more important is that in the whole planning process is that you really talk to a knowledgeable consultant, and I know there are a couple of them in the room here, to give you advice, to assess your plans for your project, to see, okay, what kind of heating powers can you, heating requirements can you expect? Is there maybe some cooling requirement as well, even though it might not be covered by an RHI subsidy or grant? But if you can use it, and you can still save energy by also using the cooling power that is generated, and, if it's a bonus, then it's nice. Not all sites are suitable. Not all projects are suitable. That's unfortunate, but if it is, it can be a very, very energy efficient way of either heating or cooling. Make sure that you get a good hydrological survey of the aquifers if you want to use this system, because that's going to determine in the end the capacity and also the efficiency of the entire system. And please take care of the system by really putting a lot of attention into monitoring, metering and safeguarding the system, because as we saw, heat pumps are expensive, the boreholes are expensive to make, and they need to be well maintained as well. And making mistakes there can be very costly. So those are some of the key pointers I want to give to you at the end of my presentation. Thank you.